Okay, so the final talk of today is Andrea Vaccaro speaking on Ultraproducts of W star bundles.
Thank you, Brett, for the introduction. I would like to thank the organizers of the event for giving me the opportunity to talk here and especially to be here. It was very funny this morning when we were asked who knew the fields before. So I did my PhD here. I think between 2016 and 2019, not many, I don't think anybody spent as many hours as I did in this place, except maybe George. So yeah. Right, so my talk sort of picks up from where Chris left. Chris told us about his work with Stewart and their collaborators, where starting from threshold completions of C-star algebras, they developed this notion, abstract notion of thresholdly complete C-star algebra. And what I would like to do now is talk about some problems, very foundational problems about this class of C-star algebras. Let's say without context. Let's say you want to study this class and study their properties like you would study C-star algebras or von Neumann algebras, and some very fundamental problems arise. So I would like to tackle some of these. I would like to advertise some of the questions that we cannot answer and give some partial answers to this question, mainly using ultraproducts of W star bundles. So really the point of the talk will not be what's written in the title, but rather the questions. I would like to take this opportunity of having so many people which I know might be interested in this stuff to revive these questions, since they've been around for some time and maybe they've been neglected in the last year, and also to present them to other people who don't know them, especially people who are more familiar than me in von Neumann algebras. So here and there in the talk, I will present some bounties that I think are worth discussing, and I will be happy to discuss in the next weeks while I'm here. All right, so as I said, I will start from where Chris left. So a thresholdly complete C-star algebra is a pair mx where m is a unital C-star algebra and X is a set of threshold states or just traces on M, which is compact and convex. So compact, convex set of traces. As Chris said, unitality is sort of redundant here. So such that what happens, again, I'm going to just restate what Chris said, such that the semi-norm, which we call the 2 norm, defined using traces over X as the supremum of all traces on A star times A, and tau varies in X. So this semi-norm is actually a norm. And as I said, I'm going to refer to this as the 2 norm of M. So such that this semi-norm is a norm, and the unit ball of M, in the sense of the C-star norm, is complete with respect to these 2 norm. And the other definition Chris gave at the end of his talk was this notion of factorial. So we say that mx is factorial if, moreover, x is a face, a closed face. Right. So a couple of examples that you already saw, and so I'm just gonna go very quickly, just refresh. So the first one is, of course, tracial von Neumann algebras. And in this case, the term factoriality is motivated by the fact that as a thresholdly complete C-star algebra, a von Neumann algebra is factorial precisely when it is a factor. And then Chris mentioned this notion of bundle over topological spaces with these fibers. So what Chris told us about was a specific instance of a more general definition, which is due to Ozawa, well, okay, which is called W star bundle. And W star bundles are really a notion which mimics the definition of C star bundles or C of X algebras, where the fibers are von Neumann algebras, and they, more generally to what Chris gave us, can be more twisted objects. So the abstract definition is this one. So a W star bundle, let's say M over a compact Hausdorff space K is a unital C-star algebra which comes equipped with a few more things, in particular with a unital embedding of C of K continuous functions on K into the center of M, and a conditional expectation. So I'm going to identify C of K as a subalgebra of M at this point. A conditional expectation E from M into C of K, such that E is tracial and B, the unit ball in the C-star norm sense of M is complete with respect to the two norm, which is defined by this conditional expectation. So defined as like this. So you should really think of these objects as C-star algebras, which try to mimic von Neumann algebras in the fact that they have a sort of center value trace. So this conditional expectation might not, in general, identify all traces, but for those which isolate, it behaves like a center value trace. So example of this is that the one that Chris gave us before. So trivial W star bundle. So given a tracial von Neumann algebra and tau, we can consider C of sigma K n, which is the set of all functions from K to n, which are bounded and continuous in the two norm induced by tau. In particular, for such bundles, and it is so factorial precisely when n is a factor. So W star bundles, maybe it's not entirely clear, but they form, they give natural examples of tracially complete C-star algebras. In particular, if M is a W star bundle over K, then the pair M and probability measures over K form is a tracially complete C-star algebra. So here basically what we have is that if mu is probability measure over k, then we can define tau of mu of A as the integral of E of A over k. So far, so good? Okay.
Is it clear that these are different definitions?
Which one are different definitions?
The spatially complete one and the W star.
So yeah, let me say something. One important thing to notice is that when you have a W star bundle, since you start from a K which is compact and Hausdorff, the set you get here, it's always a Bauer simplex. It's a convex set such that the set of extreme points is closed at compact. And in the general definition, you don't require such a thing. X can be any Schuke simplex. And in fact, Ozawa gave us a sort of converse to this. So W star bundles can be abstractly isolated within the class of partially complete C-star algebras. So this result, it's essentially due to Ozawa, but formulated in this form, I guess it's due to Castillejos, Carrion, Evington, Gabe, Schaffhauser, Tiquizis, and White. Yes. Yeah. So, but it's important that it only holds in the factorial case. So if mx is a factorial partially complete C-star algebra such that X is a Bauer simplex, then M has, let's say, just a natural structure of, a natural W star bundle structure over the boundary of X. So in some sense, you can almost use it as a definition, except it only holds in the factorial case. Yeah.
In condition B, just to be clear, it's unit ball of M, right?
Yeah, this is a very badly written one. So unit ball in the C-star norm. I think it's false. There is an example that Chris pointed out to me at some point. I sort of forgot how exactly it goes. It's nothing too deep, but maybe, yeah, I don't remember it now, but it's just false. Right, so last example that will lead me to the first bounty I want to give is the one Chris told us about, so threshold completions, which for practical reasons are usually the reason why we're interested in these guys. So again, I'm gonna quickly recall the definition, say A is, again, unital, but not really necessary as long as the trace space is compact. Unital C-star algebra with a non-empty trace space. Then we can define the completion, the threshold completion as the set of all C-star norm bounded two norm Cauchy sequences modulo the idea of all bounded two null sequences. And here we come back to something that Shri said before. Taking this completion, taking this closure operation, does it stabilize after one step? You know, normally when you have a closure operation, you do it once, and then if you do it to closure again, you get the same object. But in this case, you naturally have that every trace in A can be canonically extended to a trace in the completion, but maybe this extension is not unique. So you might have, or at least we don't know any example, we don't know if in general this inclusion is always an equality. As far as we know, there could be C-star algebra such that the completion has strictly more traces than the one you have. Of course, every trace in A naturally extends on the completion simply by taking the limit, since each one of these is the Cauchy sequence. I guess so, yeah. So the first question is simply this one. So is the trace space of the completion always equal to the trace space of the original algebra? And in fact, more generally, this is the trace problem that Chris attempted to state before. A more perhaps complicated question, which is stronger than this, is the following: if mx is factorial, is it true that x needs to be the whole trace space? This is true for von Neumann algebras. And in general, there are situations where we know that the answer is yes. In particular, I think essentially the first time where this appeared was a paper by Castillejos, Evington, Tikuishis, and Stewart, where the answer is yes for ultra powers. Well, I should say tracial ultra powers. I will define them in a second if you don't know what they are, but were mentioned by Chris before. For tracial ultra powers of, let's say, Z-stable C-star algebras. Although you can go also with this uniform property gamma that Chris mentioned before. And more recently, and this is unpublished, Sam Evington showed that actually you don't need to take the ultra powers. This is true for any completion. Again, I'm going to say of a Z-stable C-star algebra, but what you need is much less. Z-stable C-star algebra. What you need is CPOU, these complemented partitions of unity, which are implied by uniform gamma. So these are not bounties. Bounties require a head. These are just general questions. So the bounty will be, what's the maybe first case we want to test? No, it's not. No. So in fact, the first bounty would be a trivial W star bundle. So bounty number one. What about simply? Oh, yes. So you mean with type 2-1 fibers? Yeah. I'll come back also to this later. So what Stewart is pointing out that we care about situations where if you take the GNS representation of every trace in X, what you get is a type 2-1 von Neumann algebra. So yeah, bounty is trivial W star bundle and the free group factor as a fiber. So if you replace this with R, it falls within this type of completion, so we know the answer is yes. So take this, and let's say, are there extremal traces on this C-star algebra which are not points evaluation on 0, 1, which don't come from point evaluation on 0, 1, which are not of the form So evaluation on some point x in 0, 1, and then we apply the trace of f2 or below f2. And x is in the interval. Sorry for bad handwriting. So one thing you can say, so this is open, but like the z stable, or let's say the nice regular case, actually, if you go to ultra powers, you can say something. In fact, the tracial ultra power of this satisfies that property. So let me quickly introduce the tracial ultra power. I was really hoping Chris would do it, but it's all right. So tracial, what time is it? Tracial ultra powers. So let's say you have a sequence not necessarily indexed over n of tracially complete C-star algebra. The tracial ultra power, you fix some free ultra filter. I will denote it with the ultra filter on top as it is customary. So the tracial, well, in this case, I should say ultra product, is simply defined as the direct product over all sequences such that the limit over along the ultra filter of all these two norms goes to 0. And so yeah, you have to show this is a tracially complete C-star algebra, and being a tracially complete C-star algebra, you have to associate to it certain sets of traces. And so let's call this guy just M. And the definition here is that M is usually paired with what I'm going to call, again, with some maybe ugly notation, but the concept is quite easy. This. So where this set denotes the weak star closure in the trace space of this ultra product of all limit traces. Namely, traces which have the form tau I for tau I in xi, and when applied to some sequence in the ultra product are just computed via the limit. So the first, yes.
Why say a word or two about why bounding one is hard?
Well,
Not to insinuate that it is.
no. I mean, the thing is, that's why I was hoping, like, in the audience, to have some people in the audience to give me some inspiration, because I really have no idea how to approach it. The thing is, even if you replace L by R, the proof that this actually you get the whole trace space. Well, first thing, I haven't really saw it, but I believe it's sort of convoluted. It goes through very non-trivial facts. So to me, it's very hard to imagine how and what of this algebra should I use.
The important thing is that this doesn't have gamma.
Exactly. So the fact is that when you have gamma, you have this ability to transfer properties from von Neumann algebras to tracial completions. And this, with a lot of effort, allows you to say that the answer in that case is yes. Here, all you know is that you don't have that nice tool. It doesn't really give you an obstruction. And I mean, possibly the answer should be that there are none. So one should find I think a completely different method. I just don't know which one could that be.
It's very easy to see what X should be, right? You just stick to the center, and you know that it's 16 now.
What do you mean by X? Oh.
This evaluation, right? Unless I miss something very badly.
What do you mean?
Well, I mean, if it's 16 trace,
Yeah.
you restrict it to the center.
Yeah, on the center, they all reduce to point evaluations.
So you know what X is. So this question is, can
Yes. Yes.
Weird thing that can happen.
Yes, exactly. And you know also how it restricts here, because I mean, there is only one trace. So it's all about those, like if you see this as a sort of tracial tensor product, it's all about what happens in these limits of sums of elementary tensors, which.
Essentially, the question is asking whether the trace is enough to be 2x continuous.
Yeah, exactly.
Continuous, it has to be the trace itself.
There are many ways you can approach it. Like it's also asking whether the conditional expectation you get here is the same when you go in the finite part of the double dual. If they are the same, then you're fine. If they're not the same, then you will have some extra trace. There is also this fact. I'll stop it there. I don't have enough time. Yeah. So why did I introduce ratio ultraproducts? So there is this theorem which applies to the ultraproduct of this. Which shows some scenarios where the trace problem has positive answer. So let Mi be a collection of factorial W star bundles over some compact Hausdorff spaces Ki, such that these Ki have bounded covering dimension. So I should say such that there exists a uniform D bounding their covering dimensions. Let Mx be the resulting tracial ultraproduct of these guys. So again, you take the direct product quotient and the set of traces you consider is the closure of all limit traces. Then this closure of set of limit traces is actually the full trace space. Or if you want, the set of limit traces is weak star dense in the set of all traces. So in particular, this applies to the ultrapower of that. So let me give a quick sketch of the proof, or rather tell you what lemma you need. Oh, one thing I should have mentioned at the beginning of the talk. So I'm sort of going to quote something Ilias said in his talk in Münster. All the proofs, or rather the result I present today, they really follow by carefully reading Ozawa's paper on Diximier averaging and symmetric amenability. So Ilias carefully read another paper by Simon Wasserman. So in my case, many of these questions can be, so yeah, Ozawa's paper is very good. That's what I'm saying. So the lemma you need, so sketch of proof. I'll go very quickly. So you need this, maybe I can write it here. And this is an example, maybe also to pick up on what Shri was asking earlier. This is an example of von Neumann algebra type of behavior that you can find in these situations for these algebras. So I'm going to give you a very technical example, and if time permits, more than one. So the lemma that you can prove is this one. So yeah, let M be a factorial W star bundle over a space whose dimension is D, whose covering dimension is D. And now pick an element, let's say a self-adjoint element. I think I need a contraction, which is mapped to 0 by the conditional expectation. So again, if you have the analogy with von Neumann algebra in mind, you should pick a self-adjoint element which is evaluated on 0 null traces. Then for every positive epsilon, you can find a bunch of elements, a bunch of contractions indexed. It's not important how many they are. They are 10 times D. The important thing is that their number is bounded by the dimension such that you can approximate A with commutants. I think I need some constant here. Again, not really important. In the 2 norm induced by K. So in von Neumann algebras, if you take a tracial von Neumann algebra and the tracial von Neumann algebra is evaluated as 0 null traces, then there is a result by Fack and de la Harpe that tells you that you can approximate it with like 12 commutants, or 10 commutants. Commutators, thank you, sorry.
Sorry, what? Say it again.
So if M is a von Neumann algebra, and let's say the central value traced is 0, then I can replace this 10 times D by 10 and this by 0.
Oh, no, you can do it with just one commutator.
Yes, we can, but that is not.
Yeah.
You're going to need D plus 1 if it comes.
Yeah. So the thing is, if you have a W star bundle, imagine something like this. The way you prove the lemma is first check pointwise and use the result from von Neumann algebra pointwise, and then a partition of the unity argument allows you to put them together. But you need these finite covering dimension because otherwise you lose control of the number of commutators you have here. So this is more or less the.
What's the function for the sum?
Sorry?
A minus something.
24 is just because 24 is a constant here, and I is smaller. A minus 24 sum of 10 times D commutators.
For being fussy, I suspect you need D plus 1, which equals 0.
So sketch, I will just say that you use this result by Fack and de la Harpe plus a partition of the unity argument. And for those of you who are familiar with these proofs of this, the implication of Thom's winter conjecture, where strict comparison implies Z stability, this was done by Tikuishi's White-Winter, Sato, and Kishbe-Rordam. It's the same type of partition of unity argument, except there you prove you prove property gamma. Okay, so this is one thing you can do.
I see that you don't need this fact, but just to humor you, I want to repeat that any trace you element you want factor is a single commutator.
Yeah. But what I'm saying, Fack de la Harpe applies to von Neumann algebra, tracial von Neumann algebras which are not factor. Yeah. So the other thing that I sort of didn't mention consciously is this fact here. So yeah, okay, once you have that lemma, you have to work a little bit. So I don't really have much time, but the idea is that, okay, maybe I can quickly write this. How do you use the lemma to prove this theorem? Use the lemma to get that if A is a self-adjoint element, this time in the ultra product. So say, yeah, okay, I already called it M, the ultra product. So it's a self-adjoint element in the ultra product. Then the lemma plus saturation of the ultra product gives you that A minus EA is just a finite sum of commutators. And in particular, this gives you that the supremum of, let's say, let's do this. If you compute all limit traces and you look at the supremum, you get the same value that you would get if you compute the supremum over all traces. And then a Han-Banach argument gives you that these two sets are the same. And again, the fact is that now this is in theory just zero only on the limit traces, while this being sums of commutators is zero on all traces. So yeah, one thing that this result shows is also that the ultra product of these factorial W star bundles is again factorial. In particular, the set of limit traces is the whole thing, so it's a phase. And for some time, although it was not, I mean, this question was advertised for some time, is the ultra product of factorial trivially complete C-star algebras still factorial? And if you want, I didn't mention this now, but when you study trivially complete C-star algebras, you can think them as structures in basically the language you have in phenomenon algebra. So TC C-star algebras can be interpreted as, I'm going to write L2 structures, where L2 is just a language with the 2 norm, and then the usual operation. The sorts are always bounded in norm, like you would do in tracial phenomenon algebras, but now the norm you consider is the 2 norm. And so since this is a conference in logic, maybe the right question is factorial axiomatizable? Yeah.
What about if you just say is the algebra power of factorial TC star algebra still factorial? Is that obvious?
No, I don't know. So I'm going to give a counterexample to this, which is an ultra product. But yeah, I don't know. So the answer to this question is yes. In the I will just say Chris setting. So the setting that Chris told us about was the first one. Well, okay, not the first one, but it's a nice general setting where the answer to this is yes. In fact, if you have CPOU, if you have this property gamma, then being factorial is axiomatizable. But in general, the answer is no. And the example again was maybe not particularly interesting, but it is a counterexample. So let me quickly tell you about it. So it relies on some old work by Pedersen and Petersen. And these algebras that I'm going to talk about, they were called Pedersen algebras by Elias and Tristan in a whole paper by them. So they are, so I'm going to give an example, which is an ultra product of 2 homogeneous C-star algebras. So one thing which it's sort of obvious in hindsight, abelian C-star algebras and more generally n-homogeneous C-star algebras are naturally trivially complete. In that case, even the 2 norm that you get is equivalent to the C-star norm. In the abelian case, they're actually equal because all states are traces. So, what did they do? So basically, they built a sequence indexed over n of 2 homogeneous C-star algebras, unital. AN with 2 projections such that the 2 projections are evaluated equal by all traces. In particular, they belong to the closure of the span, again, of all difference of commutators of this form. So they can be approximated by sums of commutators. But if you only use n commutators, then the approximation fails. You need strictly more than n commutators to approximate the difference of those two projections. So, but Pn minus Qn has distance in the C-star norm, has distance 1 from any sum of strictly less than n plus 1 commutators. So a couple of things, I will go a bit quickly because I'm not doing great with time. So the first thing, sort of trivial to notice, is that the 2 norm here is equivalent to the C-star norm. So here you need to put the square root of 2. And the reason is essentially that on matrices, on 2 by 2 matrices, this is what happens. And the computation eventually boils down to 2 by 2 matrices. So in particular, these C-star algebras, they are C-star algebraic bundles over projective spaces, very twisted ones, very much non-trivial, and whose fiber is constantly 2 by 2 matrices. So the spectrum of those C-star algebras is projective space of dimension n, so for each n. So you have this, so in particular, when you take the tracial ultraproduct of these things, as a C-star algebra, this is really equal to the C-star norm ultraproduct because the two ideals, the ideals of 2 null sequences modulo the ultrafilter and C-star null sequences modulo the ultrafilter is the same. So if you now take P to be the projection given by this sequence of projections Pn, and Q being the projection given by this sequence of projections Qn, you have that P minus Q is annihilated by all limit traces, because on each coordinate it can be expressed, it can be approximated by a sum of commutators, but it's not annihilated by, it cannot be approximated by a sums of commutators in the ultraproduct. So in particular, so cannot be approximated by any sum of commutators in the ultraproduct. This implies, so let's call it just M as usual. This implies that the trace space of M strictly contains, let's say, just the Weak-star closure of the set of all limit traces. Again, the reason is that you have an element, a self-adjoint, which is annihilated by all traces here, but not by all traces here, because otherwise it could be approximated by this. So how do you show that this is not factorial? Well, suppose, so let's call it X. Let X be the Weak-star closure of these limit traces. And suppose it is a face. So if it is a phase, this is a standard functional analysis thing. There exists, well, first thing, take some trace which does not belong to this closure of all limit traces. And so we know there exists a positive affine function such that f is 0 on x. So let's say the restriction of f to x is 0, but f of sigma is 1. And now we know that in C-star algebras, when you have a positive affine function, you can always sort of approximate it with you can find a positive element which up to epsilon is equal to f on all the trace space. So there exists a positive element in the ultra power such that tau of A is smaller than, say, 1/4 for every limit trace, but tau of, sigma of A is greater than, I don't know, 3/4. And this is a problem because now you want to use that fact over there. Remember, the 2 norm on 2 homogeneous C-star algebras is equivalent to the C-star norm. In particular, these gets carried in the ultra product. So in the ultra product, the 2 norm and the C-star norm are equivalent up to a factor which is square root of 2. So if these traces are all small, so let's say this is a B star B, right? So let's say there exists B. This implies that the norm of B is smaller than maybe, I don't know, well, strictly smaller than 3/4. I should do the computations. And this will contradict this because now sigma is a trace, so it's a contraction. So you cannot separate them with an affine function because otherwise this affine function will have a very small norm. So it's exploiting in a very strong way that the fibers are type 1. And so the 2 norm and the C-star norm are equivalent. So really, the question is, the answer to this question is no, but as Stuart pointed out earlier, when we work with thresholdly complete C-star algebras, we really care about C-star algebras which, well, W star bundles and more generally thresholdly complete C-star algebras whose fiber are type 2. So the question is, can we find a counterexample with type 2-1 fibers? And again, if you want maybe bounty number 2, what about this ultra product here? Again, we can look at trivial W star bundles with fibers, the free group factor, and dimension of xn increasing, since by the result that I wrote somewhere there before, if the dimension does not increase, then we know the answer is going to be no. Or why not taking what Sri was mentioning, just an ultra power where the dimension of x is infinite. So in this case, are these ultra power or ultra product factorial? We don't know. Okay, so unlike Chris, I think I will use the full hour. Am I allowed? Okay. So I wanted to finish with, so far I really only talked about W star bundles and, so yeah, one thing I didn't say is that these are not just thresholdly complete C-star algebras. And again, they're thresholdly complete because the C-star norm and the 2 norm are equivalent, so completeness follows. But they're even W star bundle. You can show they have a W star bundle structure because of Downs-Hoffman theorem. So yeah, the answer is no about the non-axiomatizability or factoriality fails even for W star bundles. But yeah, I only talked about thresholdly complete C-star algebras in a purely abstract setting. So what I want to do next and finish is maybe do something which has more of a model theoretic flavor and show how thresholdly complete C-star algebras can be used to say something interesting about first order theory of C-star algebras.
I want to make a small remark.
Of course.
The reason I said that ultra power was that's a very beautiful question about Schumann factors. ultra product of non-property gamma one factor, whether it has property gamma or not.
Yes.
But then if you say just ultra power, then it will not have property gamma by Kahn's theorem.
Yeah.
Maybe you can look at Kahn's paper to get some inspiration.
I'm sure I will find inspiration in any of Kahn's paper, but yeah. Or you can explain it to me. Okay, so the last thing, so this is a general vague problem I thought about, especially when I was in Paris, and we work about this with Alessandro and Ben. And the problem is that within the context of classifiable sister algebras, so let me just say it this way, understand how model theoretic information, and here I mean just first order theory, yeah, gets transferred between classifiable sister algebras and their Elliott invariants. But here, yeah, you should take this problem and question as, I mean, I don't have a precise statement. There are situations like purely infinite sister algebras or AF algebras where the Elliott invariant is a discrete structure, so has a natural model theoretic interpretation. And in that case, you can make sense very precisely of this question, like if the sister algebras are elementarily equivalent, are the K0 and K1 elementarily equivalent and vice versa? So a little bit of advertisement here. This will be discussed, something like this will be discussed tomorrow by Ben de Bond, I think after lunch. So relation between AF algebras and their K0s on a model theoretic level, but it will be sort of beyond the first order setting. It turns out that if you go in infinitary setting and use games, things get easier. So what I want to do, what I want to close with is showing how this whole setting of partially complete sister algebras can be used to prove the following theorem. So say something interesting about the first order theory of just sister algebras. So let AB be two unital sister algebras such that they are elementarily equivalent. So in this case, I really mean as sister algebra. So I will write down in the language LC star as opposed to the language L2 that I wrote somewhere and then erased. So if they're elementarily equivalent as sister algebras in the usual language, and they belong to a class where the Kunz-Pedersen null set is definable, and this is the set that I wrote somewhere before. This is just the span, the closure of the span of all the differences of commutators of this form. An example of these classes are exact, for instance, exactly stable sister algebras, or sister algebras with strict comparison. So if you have two such sister algebras, then the first order theory of the sister algebra remembers some of the topological properties of the trace space. In particular, it remembers whether it is a Bauer simplex, and you actually get elementarily equivalence in that, and in that case, so if the boundary is closed, is compact, you get that the sister algebras, the abelian sister algebras of continuous functions over the boundary are elementarily equivalent. So in general, there's not an obvious model theoretic interpretation of the trace space, but in the Bauer simplex, this is an option. And this result shows that elementary equivalence here implies here. In particular, for instance, if any of the two boundaries has finite covering dimension, then the other one will also have finite covering dimension, and the dimension is actually the same. This result generalizes something that was done previously in the memoir on model theory of sister algebras, where something similar was shown for monotracial sister algebras. And well, let me just say a couple of things maybe. I'd rather say what's the last question instead of going through the proof. So this is C, continuous function over the extreme, the boundary of the trace space, delta E extremo T of A, and then this is elementary equivalence. So let me go through maybe the this Kunz-Pedersen null set being definable. I will not say exactly what it means, but if the Kunz-Pedersen null set is definable, this is something which is basically necessary to say anything, because it provides you with a bridge that allows you to go from there, elementary equivalence at the sister level, to elementary equivalence of the threshold completion. So if this is true, then having that A is elementarily equivalent to B implies that the threshold completion of A is elementarily equivalent in the L2, in this case as L2 structures, to the threshold completion of B. So really, the theorem takes place in this world again. And what happens is that, if PA is Bauer, then again, using methods that appear in Ozawa's paper, you can show that the center of the tracial ultrapower of A, which is really the tracial ultrapower of A, which is the same as taking the tracial ultrapower of the completion. If you take this is exactly continuous functions over the boundary ultrapower. And this is a result analogous to the one you have in von Neumann algebras, which was proved by Elias Brad and David Sherman. So if you're in this situation here, it means the two ultrapowers are isomorphic. And in particular, you get that the centers are isomorphic. From there, you have to argue a little bit that also if you know that one of the two has Bauer tracial simplex, it's not enough to know that the center are isomorphic to conclude that also the other has Bauer simplex, but you have to do a small argument, which is nothing special, but basically the heart of the proof is this. So I want to conclude with the last bounty, which is here we have elementary equivalence on sister algebra carries some information at the level of trace spaces. In a reasonable setting, can we get a vice versa? So the question is, if A and B really, I want to say if they have CPOU, but I will say if they are Z-stable and nuclear, and unital, let's say, and both trace spaces are Bauer simplex. So like at the moment, I have no idea how you would make sense of model theory and trace spaces outside this case. So these are Bauer simplices. So let's say just take. Can we prove something like this? That elementary equivalence at the level of the boundaries, does it imply that A, well, not A and B, but rather the threshold completions are elementarily equivalent in the L2 language. There is no hope to go beyond that. And so again, since bounty wants a specific head, bounty number 3, if C of X is elementarily equivalent to C of Y, is it true that the trivial W star bundle with fiber, the hyperfinite to 1 factor, is elementarily equivalent in the L2 language to this other one? And this question really, I think, I don't think Said is around, but Ilyas can maybe refer to him. You can see trivial W star bundles are as tensor products, so it sort of links also to all this big problem of how elementary equivalence gets remembered when you take tensor products. So yeah, this is all I want to say. Thank you very much for your attention.